Alright, welcome to another AQA A-Level Chemistry video. This is going to be a part 3 video on commercial application, or really I should say a part 2 on exams for questions related to that topic. I wanted to make this video because I want to separate this video into 3 because I didn't want to make it too exhausting for you guys. I want to make a real emphasis on exam practice because that's what's the most important, right? So I've got a couple of questions here, random from different papers. I probably will do a commercial application full video at the end of this unit. I've still got acids and bases to do. I want to cover that content. I won't really want to cover the content before the end of April, really. Again, most of you guys would have done your exams by then, but yeah, that's what I'm planning to do this. So I just wanted to let you know, guys, the plan about these videos. So I'm gonna first of all allow you to see the exam question for this. So, and as I allow you to see all the questions for this, I'll make you do some of these exam questions, and then so you do all the exam questions, sorry. And this is 33 minutes, by the way. It's 33-minute paper. Or it's 33 marks, really, I should say, but 33 minutes you should be spending on that. And then I will go through the video once I've paused it and allowed you to go and answer the questions. And then I'll look at the mark scheme at the end. Yeah, but also, guys, leave comments in the video about how you feel about these videos. So if you feel like these videos are too boring or too long, or you do like the videos, I don't know, just let me know. Don't be shy. Like, it can be as like harsh as possible if you think like it's not as helpful, or think I should do it a different way. I want to try and make videos that are like a bit better for you. I don't know. I just thought I just asked it because I've got a couple of the comments and they're really helpful for me, and yeah, so that's what I say. So I'm just gonna do this video and then we'll see. Let's set a timer then. So 33 minutes, 5 seconds. Let me get on my watch as well. Alright. So pause video. Oh, actually, no, I should have said. Alright, done. So pause the video now and try and answer those questions that I had here. That's from the previous video, wasn't it? Try and answer those questions. And then once you've done that, I'll answer the questions. So pause the video now, try and answer those questions. I assume you've done that now, so now I'm going to go to this and I'm going to set the timer. So I'll go now. Okay, so I use this such as rubber. Some people prefer to use just the reason for this. Oh, it's just to remove the oxide layer. Remember, this is aluminium, so exposed to oxygen will rust. So we want to remove. That rusting is aluminium oxide. So we want to remove that oxide layer. So we just get pure aluminium. We don't want it to react with aluminium oxide. One mark there. Draw a label diagram to the apparatus for a hand electrode in a cell. You don't need to include the salt bridge or any electrical circuit. So that's just, it's okay. It's just the standard hydrogen electrode. Okay, so I'm just gonna draw that. Let's not try to make it too fancy, but I will be as accurate as possible. This would be our platinum. Oh. Our platinum electrode. Our platinum. Yeah, platinum electrode. Let's color it in because just to show that it's an electrode. It's not see-through. Platinum is definitely not see-through. So I'll just do that. This is a 2-mark question, so you want to try and spend 2 minutes on this. So that's colored in enough. You don't have to do the chamber, but I usually do the chamber to show that how we're going to expose the chamber to expose the cyanohydride electrode to hydrogen gas. That's why I always do the chamber. But as far as I'm aware, you don't actually need to do the chamber. But I don't think they'll take away marks from you for doing the chamber. And now we can just start labeling. So H2 gas at 100 kilopascals pressure. Going in here. Terrible fiber. You can see you can already see what's going on here. It doesn't have to be a Picasso. Platinum electrode. And then 1 mole per dm cubed. HCl. Probably spent more time than I needed to on that question actually. But yeah, try and aim for 2 minutes on that. A simple salt bridge can be prepared by dipping a piece of filled paper into a potassium carbonate solution. Explain why such a salt bridge would not be suitable for this use. Because you have aluminium ion in it and you have carbonate ion. So the carbonate ion would react with Al3 plus, forming Al2CO3 of aluminium carbonate, reducing the concentration of Al3 plus. Affecting the results. Can I just put on that question? 5 minutes? Yeah, 5 minutes, that's fine. Fuel cells are an increasingly important energy source for vehicles. Electrode potentials. Some electrode potentials are used in understanding some familiar chemical reactions, including those in fuel cells. Following table contains some standard electrode potential data. A salt bridge was used in a cell to measure electrode potentials. Explain the function of the salt bridge. Is to allow. All these questions are always the same thing, just to allow the free movement of ions. To allow the free movement of ions in the ionic solution. To allow the free movement of ions to move through the salt bridge. To maintain charge balance. Use data from table to deduce a halide ion with the weakest reducing agent. So I think of it as strongest oxidizing agent. So that's the strongest reduced, the one that's able to be most strongly reduced, so the most positive. that's F2, but it's a reducing agent. It has to be a reducing agent, so F minus. So I'd say F minus. Use even to justify why sulfate ions shouldn't be able. I've done these questions before. I probably have. Use data to be able to justify why sulfate ions shouldn't be capable of oxidizing bromide ions. Because the electrode potential of, it's 1 mark question, so I can give a 1 mark answer. Really, because the electrode potential of SO42 minus, yeah, I can just say SO42 minus. Is less than the electrode potential of, is it BR2? Because it's BR minus, should be on the outside. Yes, sir. Yes, sir. All right. Use even to calculate a value for EMF of hydrogen oxygen fuel cell operating under alkaline conditions. Yeah, I think I have done this question before, probably, but it doesn't matter. I'll just do them again. Alkaline conditions. So that is this one here and this one here. 0.4 minus 0.83. So 0.4 minus 0.4. Make it in big writing because we can do it. Minus 0.83. And that's equal to 1.23 volts. Quick maths there. Anyway, there are 2 ways to use hydrogen as a fuel for cars. One way is in fuel cells to power an electrical motor. The other is in the fuel cell in internal combustion engines. Just a major advantage of using the fuel cell, because fuel cells are more they're more energy efficient. So fuel cells. No, wait. Yeah, fuel cells are more energy efficient. As they convert more of the chemical energy into kinetic energy to move the wheels. Yeah, same bit of time on. I actually spent 5 minutes on a question. So, associated okay. In terms of electron state, with the meaning of an oxidizing agent. An oxidizing agent is known as very strongly reduced. So it's an electron acceptor. Yeah. In terms of electrons, says this here. So an electron acceptor. If it's being reduced, it's an electron acceptor. Don't get confused with being oxidized. It's not oxidized. It's an oxidizing agent, which just means it's getting reduced. Just the identity of the weakest oxidizing agent in the table can be used to make this deduction. Okay, so it means the strongest reducing agent. I always do this. This way it always helps me out. Strongest reducing agent, which means it's very good at being. It means it's oxidized very strongly. It means it's very negative value. So CD, but it's I would say CD, but it's an oxidizing agent, so it has to get reduced to cadmium hydroxide. Explanation: it has the lowest electrode potential. Right. I always do this one because I like doing the opposite. So strongest reducing agent, which means it's the one that's going to be oxidized the greatest, so it's the most negative. But I have to remember it's an oxidizing agent, so it's being reduced. So I'd have to go in the reduction way. So that's why I'd pick cadmium hydroxide there. The diagram shows a non-rechargeable cell that can be used to power electronic devices. The relevant half equations for this cell are equations 2 and 4 in the table above here. This is the one that looks like the Daniel cell, remember? So don't worry about that too much. This is relevant ones, so 2 and 4. Okay, great. Calculate the EMF for this cell, so 2 and 4. So 2 and 4, 0.74 minus minus 0.76. 0.74 minus minus 0.76. I can just see from here, that's like doing 0.75 times by 2, and that's just 1.5 volts. Write an equation for the overall reaction that occurs when the cell discharges. So discharges is what you'd expect, just when the battery is being used. So this one has the higher electrical potential, it's going to go in that way. This is more negative, so it's going to go in the oxidation pathway. But this has double the amount of electrons, so that's to times that by 2. So if I did this up here, I'd say 2MnO2 plus 2H2O plus Zn goes to form Zn2 plus 2MnO OH plus 2OH, so just 2OH minus. I did read that. Yeah. So 2MnO2 plus 2H2O plus 2MnO2 plus 2H2O plus Zn goes to form Zn2 plus 2 hydroxide ions plus 2MnO OH, if I'm not mistaken. Yeah, great. So the juice one essential property of the non-reactive porous separator labeled in the diagram. Remember, this is just acting as a what's it called, a salt bridge. So it just allows, just think of it like a salt bridge. Remember, non-reactive porous means holes in it, and that just means it allows free movement of ions. So think of it like exactly like a salt bridge. There's nothing crazy here, and nothing different. It's just the same as a normal cell, right? So it allows free movement of ions through it. So just the function of the carbon rod in the cell acts as the anode. See here it's positive, so it's just acting as the anode. The zinc electrode acts as a container for the cell and is protected from external damage. It's just why a cell often leaks after being used for a long time, because the zinc gets reused up as it the zinc gets you, because the zinc's being reduced, right? Is it being reduced? Yes, the zinc should be getting reduced. No, it's being it's being oxidized. Sorry, it's being oxidized. My bad. The zinc's being oxidized. Yeah, the zinc's being oxidized here, so it'll get used up over time. So the zinc gets used up over time as it gets oxidized. Forming spaces for leaks. Good. All right. The rechargeable nickel cadmium cell is an alternative to the cell shown in part C. The relevant half equations for the cell are equations 1 and 3 in the table above. To use the oxidation state of this in this cell after recharging is complete. Write an equation for the overall reaction that occurs when the cell is recharged. Okay, so recharge is different. So let's just say, so let's find oxidation state. So we said 1 and 3, right? 1 and 3, and it said to use oxidation state of nickel in this cell after recharging is complete. So 1 and 3. Just clear all that. Reality in your exam, you only I just wrote up there so you can see a bit of space, but yeah, hopefully it doesn't come. So 1 and 3. What did they say? They said use oxidation of nickel. Recharging. So that's not what you expect. It's the reverse of what you'd expect. So the reverse of what you expect. So this has a lower electrode potential. So the opposite of this will be most likely to get reduced because of recharging it or putting in energy to counter it. So that's one going to be getting reduced, and this one's going to get oxidized and that's that. So the electrons here, there's double the cadmium has double the amount of electrons, so we have to double the amount of electrons in the nickel equation. So cadmium hydroxide plus 2 NiOH2. Oh, sorry. Plus 2 OH minus goes to form cadmium plus 2 hydroxide ions plus 2 NiOOH plus 2 H2O. You can just cancel out these 2 hydroxide ions, and that is it. And that's that. Now they said what's the oxidation state on nickel after it's being the of nickel is after it's recharged. That is x minus 2 plus minus 2 plus 1 equals 0. That's just x minus 2 minus 1 equals 0. X minus 3 equals 0. X is equal to plus 3. You should know about how to work at oxidation states by now. I did that in the video a long time ago on inorganic chemistry. To write an equation for the overreaction that occurs when the cell is recharged. Well, I've already done that. By the way, you could already see, you didn't have to write the equation to go do this first part here. I just done it because I saw the second question. But realistically, we've already done the second. But you could just see that this one is going to go in this direction here. We can see that this is going to be the one that we're going to look at first. But yeah, I've already done the equation now. So cadmium hydroxide, so CdOH2 plus 2 NiOH2, and then also some cadmium. I believe there's something along those lines there. Yep. State one environmental advantage of this rechargeable cell compared with the non-rechargeable cell described in part C. It means that we can reuse the same batch. One environmental advantage. Actually, only the one use I say less waste in landfills. Less waste in landfills. All right. An ethanol oxygen fuel cell may. Sorry about this. So an ethanol oxygen fuel cell may be an alternative to a hydrogen oxygen fuel cell. When the cell operates, all of the carbon atoms in the ethanol molecule are converted into carbon dioxide. Deduce the equation for the overall reaction that occurs in the ethanol oxygen fuel cell. Right, so ethanol oxygen fuel cell. Sorry, I'm also streaming whilst doing this, so bear with me. So ethanol, CH3, CH2OH, plus what? So oxygen, all of the carbon, so two CO2s, right? Plus water. This is the only way I can balance this out. Now we have 6 hydrogens, so this should be 3 H2O, right? That balances out. CHO. I always do it like this because it always helps me out. 2, 6, 3, 2, 6, 4, 5, 6, 7. Alright. So 4, and then yeah, 5, 6, 7. I can add, if I add 3 to make that 6, and that's 7, yeah, so 3 O2 here, 6, 7, so then that's balanced now. There's use of the half equation for the reaction at the ethanol electrode. In this half equation, the ethanol reacts with water to form carbon dioxide and hydrogen ion. So CH3, CH2OH, with water, so to form carbon dioxide, so 2 CO2, and hydrogen ion, so 3, 4, 5, 6, 7, 8. I'm just going to put H plus just for now, right? CHO, CHO, 2, 8, 2, 2, that's 4, no, sorry, oxygen is 4, hydrogen is just, so this needs to be doubled to that, first of all. That's the one I can see most blatantly first. If I do that, the oxygen now becomes, the oxygen now become, no, but that's just now 3. That's 4 now. Yeah, that's 4. So the carbons haven't changed. Hydrogen, now all I have to do is just do the hydrogen now. So that's 3, that's gonna be 6. That's 12 in total now. I don't like the way that H is done. 12 H plus, balanced there. The EMF for the ethanol oxygen fuel cell is 1. Use data from table to above to calculate the value for the electric potential of the ethanol electrode. For the value of the ethanol electrode. So oxygen is 1.23. How do you know what is ethanol being reduced, did they say? Or oxidized? Was forming, we know it's equal to 1. Water's being split, so I can see that's being oxidized. So ethanol's being reduced, so it's 1.23. So I think ethanol's being oxidized. So 1.23, yeah, 1.23 minus 1. Wait, 1.23 minus x. So x is equal to 1.23 minus 1. So wait, 1.23 minus x equals 1. Therefore, x is equal to 1.23 minus 1, and that's equal to 0.23 volts. Always put a circle around that or box. How much time I've got? 5 minutes, 26 seconds to do all of this. Have I been wasting time? I probably have been wasting a bit of time. It's just why an ethanol can be used, can be considered to be carbon neutral fuel, because ethanol is produced from fermentation. From plants. CO2 released from atmosphere, released into atmosphere, is used up by plants for photosynthesis. Right. Half equation for the table of zinc and oxygen are simplified. Simple diagram of hearing aid cell shown with figure. Using it to calculate the EMF of the cell. So air hole, zinc, stainless steel. These are the only two that make sense for me, because I can see oxygen there. So 0.4 minus 1.25. So that's equal to 1.65 volts. Use the half equation for the table to construct an overall equation for the cell reaction. Okay. That's double this. So 2Z, actually put at the very bottom here. 2ZNO. No. What am I doing? First of all, that's going in the oxidation way. So it is O2 plus 2Zn plus 4 hydroxide ions goes to form plus 2H2O goes to form, that 4 hydroxide stays the same, 2ZNO plus 2H2O. Now the H2Os cancel out and the hydroxides cancel out, so it's O2 plus 2Zn goes to form 2ZNO. Time I've got left, 2 minutes 22 seconds. Identify which of A and B in the figure is a positive electrode. So the anode, so that would be reduction. No, oxidation. So which one's being oxidized? The zinc one, so B. Because the anode's where oxidation happens, so B. Reducing because it's next to zinc. The zinc paste which has a more negative electrode potential. Sorry for the noise in the background. More negative electrode potential. So oxidation is more likely. How much time have I got left? Just under a minute. Okay, I've got enough time. Just one reason why, other than cost, why this type of cell is not recharged, because the reaction isn't reversible. Okay. isn't reversible. Hopefully it's correct. I've never done this question, so bear with me on this. I think that's correct. Yeah. Just make sure you have better handwriting than me. There you go. That should be it. Alright, cool. I'm going to go through the mark scheme of this question now. So, wait 1 second. I shouldn't have. Let me just do this here. Maybe I shouldn't stream whilst doing these videos. Alright, cool. This one? Where did this question have come from? I don't remember where I took this question from. Let's just hope I took it from here. Question is at 2. So no. This. Yes, I did take it. So it's this from here. Mark scheme. Good. Hold on. Battery's going to go out, so I need to get my... Alright, so go through this here. Go through the mark scheme. So question 2, remove the oxide layer. So yeah, for this question here, you have to understand that it's part of your understanding of what that aluminium is a metal and that it reacts with oxygen. So, and we don't want aluminium oxide, we want to react with pure aluminium. And when you see aluminium, that's, or any metals in general, right, that are left in oxygen over time, even cars, right, if you ever like scratch a car, if you ever scratch a car and you expose, because the paint really is acting as a coating layer to prevent the car from being, even a silver car, right, it's still painted onto because you don't want the metal to rust, you don't want the metal to be exposed to oxygen, you don't want it to rust, right? So if you ever scratch a car, right, and you don't take care of it, that metal in the car will then rust over time, because now they're probably making some sort of alloy or whatever, but realistically it would rust. So if you're just doing an experiment where you're having an electrode and you've left it out into oxygen for a long period of time, what you want to do is to remove the oxide layer, which will be on the surface. The inside won't be affected, but the surface of that aluminium will have an oxide layer on it of aluminium oxide. So you want to rub it with sandpaper to remove the oxide layer. If you've seen rust, you can easily move away once you dust it off with some sandpaper. And yeah, so that's what you're just trying to remove the oxide layer so we can react with pure aluminium, so aluminium can be oxidized for this reaction here. Is that being oxidized? Yes, 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 it is. Good. Alright. That. So an appropriate method of delivering a H2 gas over a platinum electrode. So this is an appropriate method of delivering H2 gas. So it needs H2 gas and platinum electrode labeled. H2 gas is labeled here. I've showed how it's coming in. So that's that. Platinum electrode is labeled. Yes. Platinum electrode must clearly be in contact with the solution of the named acid. Yes and yes. So it's in contact, yes, and named acid, yes. That's 2 marks there. The carbonate, so the next one, the carbonate ion in the acid reaction, so, or in the, the carbonate ion reacts with the acid in SCHE. Reaction given below / reaction between carbonate and Al3 plus. Okay, so, oh, they wanted actually to write out the, I actually wanted you to write out the equation. H plus slash AO3 plus. Oh, okay. So I've said that the carbonate ion would react to the AO3 plus. So it does say slash reaction between carbonate and AO3 plus. So the carbonate would react with AO3 plus, right? And I also said that it would reduce the AO3 plus concentration changes. Well, I've said it would reduce the concentration of AO3 plus, which would affect the results. I don't see why. I've said it's changed, really. When you're reducing the concentration of AO3 plus, aren't you, really? I wouldn't give... My teacher gave me a mark for this one. Maybe my teacher was wrong if I was giving me the mark for that. Speak to teacher about this. I think saying that it's reducing concentration is showing how it's changing. But speak to teacher and don't make the assumption for that type of question. But reducing the concentration of AO3 plus affecting... The idea is that the concentration of AO3 plus is changing. This is just change is enough to say. I said that it's reducing the AO3. Well, that's what's happening, really. You're reducing the concentration of AO3 plus because it's reacting with the carbonate ion. Yeah. I'd personally give that, but again, talk to teacher about that. Your teacher's usually always right. And I'm going back to question 1 here. The ions in salt bridge. The ions in the ionic substance in the salt bridge move through the salt bridge to maintain charge balance. So to allow free movement of ions in the ionic solution, to allow free movement of ions in the ionic solution to move through the salt bridge, that's a mark, and then to maintain charge balance, another mark. 2, what's that there? So 5 out of 5 marks for that one there. F minus, yes. I don't think I need to explain some of these ones. I think I've already done this one before. Yes. Okay, this is one I haven't done before. So a fuel cell converts more available energy from combustion of hydrogen into kinetic energy. So as they convert more of the chemical energy, into kinetic energy to move the wheels. I won't give myself a mark here because I've been too lenient with myself. Give myself 5 here. I've said the right things here. They may accept, they may not. But I always try to be realistic. So fuel cells. I have to put two L's here. Fuel cells convert fuel cells convert more of the available energy. I mean, saying it's more efficient is showing you're using more of the available energy. Okay, anyway, more of... Does it allow efficient? No, it doesn't. This is what I mean, like, this is really saying the same thing, but I mean, as I said before, I mean, go off what your teacher says and always follow the mark scheme because AQA don't care if it's technically correct. They want what's on the mark scheme. So fuel cells convert more of the available energy from combustion of hydrogen into kinetic energy of the car. Really, that's the wheels. Move on. Now where did I get this from? I think this is from a different question now. From here. Is behind door number 2. A brand new car. Anyway, yeah. Mark scheme. Electron acceptor. This here, lowest electro species on the left hand side with the least positive or most negative electro potential or lowest electro potential. .5 volts. 2 MnO2 plus 2H2O plus Z then goes from 2 MnOH plus 2OH minus plus Zn2 plus. Great. It allows free movement allows ions to pass through it, or all words to that effect. So just anything relating to that. It allows free movement of ions through it. That's the same thing. Next one is allows electrons to flow, makes electrical contact. It does say allow act as an anode. Doesn't prefer it, but it says you can say that, so that's a mark there. Number 5. Zn is used up. Zinc gets used up over time. It gets oxidized. Yeah, you're saying the right words there. Next one is +3. CdOH2 plus 2NiOH2. 2Ni. Yeah. Yes. Correct. 3 marks there. It's balanced as well, so that's fine. That's 2 marks. Metal in use, supplies are not depleted. Can be reused. No landfill problems, or less waste in landfills. I'm gonna accept that one because that's you saying that in the textbooks it always says less waste in landfill, so I'll give myself that. But I think the better ones here are metal compounds are reused. I think that's, I was about to say that the batteries can be reused, but I was like, is that really an environmental, is that the way that they want me to answer it? So I guess technically yes, so the metal compounds are reused, so that's a massive M. Massive. That's just correct. I forgot that this is a half equation. That's why I was like, oh, something's wrong here. It's a half equation. I was spending a lot of time in this question because this is not a mark here. I was like, this is a half equation. Why is I have not got electrons? And then I didn't think about it. So I was like, something's wrong here because it's a half equation, right? Now, how am I gonna know if it's reduction or oxidation? But yeah, I clearly forgot about that. 12 electrons is a half equation, so it's got to show oxidation or reduction. I just assumed it from here because it's forming H plus, so it must be from H2O, so must be some sort of oxidation here, but yeah, that's my bad. 0.23 volts, yes. Ethanol is produced from CO2 released by combustion, fermentation. Ethanol is produced from fermentation from plants. CO2 released from the atmosphere is used up by plants for CO2 taken up by photosynthesis. So I'd say, was that 16? Is this from a different question? I think it might be a different question. Maybe it's the wrong one here. Where did I get this question from? Mason. Sorry, I was trying to find where I got this question from, and it was. Oh, here it is. Here, I sounds like I'm just being blind. What's this now? Question? Was this question 1? Was this paper 1? Mark scheme? Yes. Yes. This is 1.65. Yeah. O2 plus 2Zn goes from 2Zn. Oh, fine. Oh, it's A. Also, positive electrode. Positive electrode would be more reduction. I'm losing my mind, aren't I? I'm losing my mind. Yeah, it would be A. I guess it always guys, or just drink water. Everyone just drink water, man. Maybe I'm just tired. I don't know. Just making silly mistakes now. Positive electrode. So that'll be A, because that's where that's more likely to have reduction, because at the anode, if it's more positive, so the more positive electrode is where reduction is more likely to happen, because it's more positive, so more likely to have reduction at that stage. The next is zinc plate, yeah, and that's going to be because the O2 electrode is more positive. O2 electrode has a more... My handwriting is so poor. Has more positive electrode potential for reduction. That and reaction isn't... Cell reaction cannot be reversed. Reaction is reversible. There. One, two, three. I mean, that's not really 40 marks, just this part here. So, 3, 4, 5. 3 out of 5 for this. So 3, that's 19 now. $24. 29. 29 out of 33, not too bad. Hopefully this video was helpful. And yeah, that's